So now that we have learned how to describe surfaces with parametric equations, so we can describe, in a sense, all surfaces, now we're going to look at how to do surface integrals. So let's, as always, pause a moment to think about what we already know to see where this might come from, how this might be the next step of something. So previously, we saw how to take an integral over a one-dimensional parametrized curve, and we could write that equation as r equals x of t comma y of t. I guess we should really be thinking about this three-dimensionally, so let's just say comma z of t. Okay, so like that. So next, and we saw a couple different types of integral that we could take. So first of all, if there's just no function, we could simply say that we're finding the arc length, and that was the integral over the curve, just ds. And then in order to calculate that, we would write that out as the integral from a to b of the absolute value, or the magnitude, I should say, of dr dt, and then all of that dt. Then we also have the scalar line integral. So the integral over the curve of some function, ds. And when we write that out parametrically, you just get the integral from a to b of your function f times, again, magnitude of dr dt, all that dt, times dt. Next, we saw, and then that scalar line integral could represent, if you think about the function as a height over the curve, it could be an area, or if f was a mass density, then you're finding the mass. Those are possibilities. Okay. Next, we talked about vector line integral. So that was the integral over the curve of some vector field f dot dr. And written out parametrically, it would look like this: the integral from a to b of vector f dot dr dt times dt, or written out using ds, it would be in this integral over the curve of f dot unit vector t, unit tangent vector t ds, or written out in coordinate form, it'd be the integral over the curve of p dx plus q dy. In other words, if you write out the dot product. Okay. And then also, and that sort of represented some sort of flow along the curve. It could also represent work done by the vector by some force field F along the curve from starting point to ending point. Also looked at the flux line integral, and that was just sort of the same thing, but in the perpendicular direction. So, oh, that's not it. Let's see. Sorry, it needs to be like that. Okay. So it work out like this. Okay. Now, let's see. So a little recap here. Yeah, so that's a little recap of what the thing we were doing. So now we're going to do all of these things, but we're going to, again, just like we did last time previously, kick things up a notch, another dimension. So how does that work? Let's take a look. So we're going to focus on right now is talking about what would a scalar surface integral be? What would it look like? Okay. So building it up the same way we built it up last time, we're going to think about if we have a little bit of surface, which is ds. Now S is big S. Big S, we think of that represents a two-dimensional surface. We use little s to represent a one-dimensional curve. So ds with big S, we're going to need to figure out a way to convert that to dA, and we're going to think of A as being our area from UV coordinates. So dA we can write out as dA is just the same as du dv. Okay, that's the first thing. Second thing is that I should say, first of all, that will allow us to calculate surface area. Next, we know that once we can convert ds, which is sort of like a little bit of the surface along the surface itself, once we know how to convert that to dA, then we can convert any integral, so it could involve, the integral could involve a function as well. Okay. So in order to do that, let's first talk about how to switch over ds in the same way we previously did before. a similar way. So let's talk about how to find surface area. So let's remember that we already know how to find surface area in a simple case, in a special case. The special case was if the surface can just be described as z equals f of xy. In other words, you don't need parametric equations. Z is just a function of x and y. So in that case, what we previously saw is that the area of the surface is just the double integral of ds. In other words, it's adding up all the little bits of surface area. And that can be written out as the double integral over the region, where the region is the x and y values from the domain, of the square root of df dx squared plus df dy squared plus 1 square root of all that, and then dA. So we previously did that. And recall where that formula came from. So that formula came from the fact that we found the two tangent vectors, and then we took the cross product, and then we took the magnitude of that. And that's what that whole square root expression was. Okay. So now we're going to do the exact same thing, but we have to do it with parametric surfaces. But this is great because we know how to do that. We know how to find tangent vectors for a parametric surface. Now that's something that we've just recently figured out. So now we're going to go through that process. Okay. So for a moment, I want to be able to show you the picture of what's going on. So you're going to kind of get to see everything at once, but I just want to take a moment just to focus on the picture. If I can get it all in here. There we go. Okay. So parametric surface. So what do we have? So first of all, remember that we've got on the left side our region in the domain, which is in UV coordinates. So imagine that we take some little rectangle of that, and that little rectangle is going to have a width delta U and a height delta and a length delta V, however you like, and that's at some specific coordinate that we're going to call UI and VJ. Okay. Now, our function R, which makes the surface, takes that whole domain and then maps it to the surface on the right. But let's focus for a moment on just that little rectangle piece of the domain. That gets mapped into the surface. Now, just the surface itself, it's going to be like some kind of like little bendy shape. So that little piece of the surface, we're going to call, so just like that rectangle was A sub ij, that little bit of area, that little bit of the surface, we're going to think of as S sub ij. But just like before, we're going to make an approximation. We're going to approximate it by saying, what if it was the thing that we could figure out the area for? What if it was the tangent plane? So, tangent plane. So the tangent plane, it's a plane, so we're going to call it P. So that little piece of tangent plane is going to be P sub ij. So now let's figure out how to describe that little piece of the tangent plane. So what are the tangent vectors? The tangent vectors, well, we know the vector itself, that we talked about tangent vectors last time, is going to be dr du. Well, the two tangent vectors are going to be dr du and dr dv. However, we've scaled them down, so each one is scaled. Remember the original bit over here. We know that dr du is going to sort of point along one side, but it's scaled by the magnitude of delta u. Same thing on the other side. The direction is going to be dr dv, but that's going to be scaled by this magnitude, which we'll take to be small, of delta v. So those are your two tangent vectors. So here's the first tangent vector is dr du, but scaled by the magnitude delta u. And then here's your other tangent vector, drdv scaled by the magnitude multiplied by the scalar delta v. And here I should have mentioned is your sort of base point of x, y, z with some particular value. So xij, yij, zij. Okay. So putting all that together, so multiplying out that vector gives you this expression for the first tangent vector and this expression for the second tangent vector. So now we've got the two tangent vectors, and now we do the same thing we did before, which is just take the cross product and then take the magnitude, and that's the area of that parallelogram, which again is the tangent plane, which is an approximation to the original surface. So working that out, that will give you the cross of those two vectors, which is right here. But remember that delta u and delta v, those are just some constants. So we can pull that outside of the magnitude of the cross product. So finally we get this. So we get the magnitude of drdu cross drdv, and then all that times delta u, delta v. Now here's where we make our super key observation. We've seen drdu cross drdv before. That was just little n, the normal vector. So now we know how to make the conversion. We know that that little piece of tangent plane, its area is going to be magnitude of the normal vector times delta u times delta v. And of course, we don't want just the area of that little piece. We want to get the total area, so we add them all up. And of course, you have to sum over all the possible u values and all the possible v values. And that's why it's a double sum. But that's the area of all the pieces of tangent plane. That's just an approximation to the area of the surface itself. So that gives us that area statement. Now, of course, we don't want an approximation. What we really want is to make an exact statement. And we know that this becomes an exact statement when deltas become d's and when sums become infinite sums or integrals. So finally, we have the area equals the double integral over the surface of ds. And that is just the double integral over the region. And remember that region means over uv values of the magnitude of the normal vector du dv. And then ultimately we could write du dv as just dA. So as a side note, one can think of magnitude. One can think of the magnitude of the normal vector, which is the magnitude of dr du cross dr dv. You can think of that as a scaling factor. So a little that little rectangle, to what extent does it get blown up or shrunk in a sense by this map? And that's what that tells you. Okay. So there's the sort of long derivation. There's the idea of where this comes from. We've gone through this process before, but we did it for z equals f of x, y. Now we've done it for the parametric formula for a surface, which is the more general case. So let's actually put this in action now. Let's see how this works in a problem. So, problem. Find the surface area of, and then here's the formula for the surface. R of uv equals u cos v, comma u sine v, comma u. And then we'll take the domain to be u goes from 0 to 1 and v goes from 0 to 2 pi. Okay. So before we start the calculation, just a quick comment. This is a reminder of what this formula actually describes. This actually describes a cone of height 1. So u plays the role of the radius r and v plays the role of theta. So notice that there's a cos v sine v, so that wraps around in circles. And then u is like the radius in front. And then also it's the z coordinate, so you're climbing as you go. You don't need that to do the problem. It's just interesting to have what graphically is going on. Okay. So now we can just go ahead and do the calculation. So first of all, the question is to find the surface area. So set up your basic surface area statement. Area is just the double integral over your surface of ds. So now what we just saw is we know how to convert ds in order to make this basically into parametric form, or re-express parametrically so we can actually do the calculation. So we know that ds just converts to magnitude of the normal vector dA. So now we have to find the normal vector in order to do the calculation. So let's go ahead and do it. So remember, the normal vector comes from first finding the two tangent vectors. So let's do that. So first we're going to need dr du, then we'll need dr dv. So dr du is cos v comma sine v comma 1, and then dr dv is negative u sine v comma negative u, comma u cos v comma 0. And then we'll need to take the cross product and take the magnitude of that. You could do that calculation on the side if you wanted. I chose to do it inside the integral itself. And we also know that dA. So how do we want to split up dA? In this case, all of the boundaries are constants. The formula doesn't look terribly funky, so you could write it as du dv or dv du. So I sort of default to always writing it as du dv. So now we've written dA in terms of our parameters, du dv, and we can now fill in the boundaries. So we're given the boundaries, u goes from 0 to 1, and v goes from 0 to 2 pi. So that's the integral that we need to do, and now we just calculate. So first of all, we need to figure out what is the cross product. So calculating the cross product, just get magnitude of negative u cos v, u sine v, u. And then the magnitude of that, working it out, you'll get u cos v squared plus u sine v squared plus u squared, and then all of that to the 1/2. And then notice what happens. You will get a u squared cos squared plus u squared sine squared. Factor out the u squared, you get cos squared plus sine squared. That's just 1. So put it all together, you'll get 2u squared square root of that. That just gives you u times square root of 2. So that actually all simplifies very nicely before you even start integrating. And now we can just go ahead and do the integral. So integrate with respect to u, and you get 1/2 u squared, and then rad u is still there as a constant. Sorry, that should be u goes from 0 to 1. Up to u equals 1, just to always be clear and precise. So u goes from 0 to 1. So plugging that in, you get 1/2 times rad 2. And now we can go with respect to v. You just get 1/2 rad 2 times v, plugging in from 0 to 2 pi, and that just gives you, when it simplifies, pi times rad 2. Okay. So there is our first basic calculation of a surface integral, and you see the way in which you can basically convert this into your parameters u and v. The conversion is ds, here we go, ds equals the magnitude of the normal vector dA, and we already have seen previously how to calculate the normal vector. It's just dr du cross dr dv. So knowing that, that tells us how to do just a basic double integral ds, and that which gives us the surface area of S. And then also, this extends into how do we do a scalar surface integral in general. If there's a function in there, that's okay. The scalar function just comes along with us. So the double integral over the surface of some function times ds. Now we just write everything parametrically. We know how ds converts. It converts to the magnitude of the normal vector dA. And we know how the function converts using the parametrization. Basically, the function is written in x, y, z, and in your parametrization, you know how to write that parametrically in terms of u and v. And let's take a moment and look at a special case. So what about the special case where the surface is described by z equals f of xy? So as we've said before, in that case, you can just use x and y as your parameters. So dr du is really just dr dx, which calculates to 1, 0, fx. No, sorry, negative fx. No, fx, sorry. And then dr dv is just dr dy, which calculates to 0, 1, df dy. And then the normal vector, the cross product of those things just calculates to negative f dx, negative f dy, 1. Therefore, put it all together, and what do we get? The norm of n is just dz dx squared plus dz dy squared plus 1 square root of all that. And therefore, the double integral over the surface of ds is just the double integral over the region, which is the region for your parametric coordinates, which in this case are x and y, of square root of all of that rad dz dx squared plus dz dy squared plus 1, all of that dx dy. So that's the special case that we've already seen before. So the parametric, again, is a general form of the z equals f of xy, which is just a special case of parametric. But now we can also look at what if we don't have z equals f of xy, but what if rather x is a function of y and z? So let's say x equals g of yz. Then you can just turn it around, and by the same process, you'll get that the double integral of the ds is just the double integral over the region of, now you'll have dx dy squared in there, and you'll have dx dz squared in there, and then the one in the first, we'll put the one in the first spot to help to remind us, and then all of that would be dy dz. And then similarly, if y is a function of x and z. And then to further connect it with the things that we've done before, again, in our special case, if z equals f of xy, we can write this in a different fashion. We can write this as essentially, we can take z equals fxy and basically write it as the contour, a contour line of a function of 3 variables. So make this z equals f of xy is some function g, and we're taking a contour line for that to get our surface function. And now we can take the gradient of g, and that actually gives us, if you just calculate it directly, negative df dx, negative df dy, 1, and that is your normal vector. And so then another way to write this would be that ds equals the magnitude of the gradient of g dx dy. So I just bring that up because previously we've used this method in order to find normal vectors for a surface written in terms of z equals f of xy. So I just wanted to make this side note to make the connection between the normal vector that we found previously using the gradient and normal vectors that we're doing now. They really are connected, and in that special case, the same method still works. I just want to mention that it only works for this special case. You shouldn't be using it in general because, let's see. Yeah, I'll just leave it there. Yeah, there are some general things that you can do, but I'll just leave it here to look at your leisure. Yeah, we won't be doing that right now. I'll just mention it. So let's calculate the scalar surface integral. So in this case, we're looking at the integral over the surface y ds. So basically y is your function. And where your surface is described by z equals x plus y squared, and we're taking x from 0 to 1 and y from 0 to 2. Okay. So the first thing is let's write down our basic facts. So we're doing the scalar surface integral, and we know that in order to do this, we're going to have to rewrite it parametrically. So the conversion is the double integral of, oh, should be y in there. Okay. So the double integral over the surface of y ds, we know how ds converts. So this is going to be the double integral over the region of the function y, and then ds converts to the magnitude of the normal vector dA. So again, remember that ds is on the surface, dA is the region where our parameters live. Okay, now, how do we make the parametrization? Well, look, this is a special case. The surface is described by z equals some function of x and y. So because of that, we know our parameters are going to be x and y, and we'll just shortcut right to the formula for the normal vector. So normal vector is negative df dx, comma negative df dy, comma 1. So calculate that out. What is, so remember so the function for the surface was just z equals x plus y squared. So negative df dx on that is negative 1. Df dy is just 2y, so negative is negative 2y, and then 1. So now let's plug all of that in. So here's what we get. So first of all, written parametrically, so normally we have to convert y to writing it parametrically, but we're using x and y as our parameters because this is the special case, so y is just y. Next, we need the magnitude of the normal vector. So 1 squared plus 2y squared plus 1 squared, square root of all that. And then dA, we could write that as dx dy or dy dx. I chose to write it as dy dx, and we know y goes from 0 to 2, and x goes from 0 to 1. So now we're all set up, so let's do this integral. Well, so first we have to simplify what we've got. So in the radical or raised to the 1/2, simplifying, that's going to be 4y squared plus 2. And now we have to do this integral dy. So looking, this works out very nicely. This is just a substitution. So we can just do that. U equals 4y squared plus 2. And then du is going to be 8y dy. So y dy is going to get replaced with 1/8 du. That's the first thing. The second thing is the way that I like to do these substitution integrals is I like to specifically write down what are the new bounds of integration. So if y goes from 0 to 2, when y is 0, then my new variable u is 2. And when y is 2, my new variable u is 18. Okay. So this is just the same as the integral. The x part stays, and now it's the integral from 2 to 18 of 1/8 u to the 1/2 du. So doing that integral and tracking the constants, you get 1/12 u to the 3/2. And again, u goes from 2 to 18. So plugging that in, you get the 1/12 again is pulled out in front, and you get 18 to the 3/2 minus 2 to the 3/2. And now I have to integrate that from 0 to 1 dx. So that's just that thing times x from 0 to 1. So you just get 1/12 times 18 to 3/2 minus 2 to 3/2. You could leave it like this, or you could do a little simplification. And if you factor things out, it works out a little bit nicely because you wind up with 9 to the 3/2, which is actually 20, which is actually 27. So you wind up with 1/12 2 rad 2 times 26. So you just get 13 rad 2 over 3, which is approximately 6.13. But again, those last couple steps were just simplifying radicals. All the calculus work was before that. Okay. So now let's do another problem. Okay. So now let's do this surface integral, the double integral over the surface of z ds. And what's the surface S? It's the cylinder radius 1 around the z-axis, and it's between the planes z equals 0 and z equals 1 plus x. So this one is definitely trickier because we're certainly going to have to write things out parametrically. So the first thing to notice is, how are we going to write the formula for the surface parametrically? Well, since it's a cylinder, that's a clue right away. You're going to want to use the cylindrical coordinate parametrization. So let's do that. So first of all, what's the standard cylindrical coordinate parametrization? X equals r cos theta, y equals r sine theta, and z equals z. And so that's standard cylindrical coordinates. Now notice that this particular cylinder has a radius 1. So therefore, the parameterization for this cylinder is just going to be r equals cos theta, comma sine theta, comma z. So notice that because we use cylindrical coordinates to describe it, sticking with that notation, our parameters wound up being theta and z. And that's fine. You can stick with that. You can always use any 2 letters that you like. Okay. So further, when we write our parameterization, we need to know what the boundaries for our parameters are. So we're given the boundaries for z. Z starts at 0 and ends at 1 plus x. But again, we're expressing everything parametrically. So x is now cos theta. So the boundaries for z are 0 to 1 plus cos theta. And what are the boundaries for theta? Well, there's no restriction on our cylinder, so it always goes, with no restriction, it'll just go from 0 to 2 pi. So that's what we have. So now let's try to get into the next part. So first of all, we got to find the normal vector. So we're going to need drdu and drdv, but of course our 2 parameters in this case are theta and z. So drd theta, if you calculate that, you'll get negative sine theta, comma cos theta, comma 0. And then we need drdz. So calculating that, you get the very simple, very nice 0, 0, 1. And then we need to take, so those are the 2 tangent vectors. And now we need to take the cross product to find the normal vector. So doing that, taking the cross product, you get cos theta, comma sine theta, comma 0. And then we know that we're going to need the magnitude of that for our integral, but how very nice, that's just going to be cos squared plus sine squared plus 0 squared, square root of all that, it just works out to be 1. Super helpful. So let's now that we have so much information that we need, let's go back to the surface integral. So the scalar surface integral was the double integral over the surface of z ds. Now let's convert everything. So we know that z, written in the new parameters, well, z is just z. That's very helpful. Next, ds becomes the magnitude of n dA. So now we know what all these things are. So we know that for dA, that just becomes, well, it could either be dz d theta. Our 2 parameters are theta and z. We could either write it as dz d theta or d theta dz. Now remember that theta goes from 0 to 2 pi, so it has constant boundaries. But z goes from 0 to 1 plus cos theta. So it has variable boundaries. So that means dz must be for your inside integral. And then we got the boundaries set up. And then finally, z is already written parametrically, so z is just z. And so now the integral is set up, and now we just go ahead and do it. So first, integrating with respect to z, you just get half z squared. And then evaluating on the boundaries z equals 0 to z equals 1 plus cos theta. Plugging that in, you get half 1 plus cos theta squared. So to integrate that, of course, you want to multiply it out. And you notice that you get a cos squared theta in there. And to do the integral of that, use the double angle formula. So cos squared theta is just half of 1 plus cos 2 theta. So make that substitution. So altogether you get half plus cos theta plus a quarter 1 plus cos 2 theta. And now we go ahead and do this integral d theta. So the integral of half is just half theta. Integral of cos theta is just sine theta. And then notice that if just quickly distributing the quarter, integral of a quarter times 1, that's just a quarter. Integral of that is quarter theta. And then a quarter times cos 2 theta. When you integrate that, because of the substitution with the 2 theta, you get a 1/2 popping out. So you wind up with 1/8, which is just 0.125 of sine of 2 theta. And now you have to evaluate on the boundaries from 0 to 2 pi. So plugging in, you get, it simplifies to 3 pi over 2. So this particular problem, just to look back, was a case where we did have to write down the parametrization of the surface. However, because the surface was a cylinder, we've already studied how to write down the parameterization of that. Those are just cylindrical coordinates. That's, in effect, a way to write down a parametric formula for a surface that is a cylinder. Okay. So next, we're going to look at another special case. So what about the special case where, as we talked about before, the surface S is a surface of revolution? And in this case, we're going to take y equals f of x. We're going to assume x goes from a to b, and we're going to evolve it around the x-axis. So in this case, I'm not going to use the parameter t. I'm just going to stick with x. So our surface has the formula r. So r is going to be a function of two parameters, x and theta. And that's going to be x, comma, f of x cos theta, comma, f of x sine theta. And since we're evolving it all the way around, theta will go from 0 to 2 pi. So now let's work out, for fun, what the general formula would be. So first, so I should say general formula in order to find the surface area. So in order to do that, we would need, first of all, both tangent vectors. So we're going to need dr dx and dr d theta. So dr dx, so looking at the function r, which remember is right here. So just take ddx of each component. So ddx of the first component is just 1. ddx of the second component is just f prime of x cosine theta. ddx of the third component is just f prime of x sine theta. Next, let's take a look at, we need the second tangent vector, so dr d theta. So dd theta of the first component is 0. dd theta of the second component is going to be negative f of x sine theta. And then dd theta of the third component is going to be f of x cos theta. So now we have our two tangent vectors. Now we need the normal vector. And we get that by taking the cross product. So taking the cross product of those two things, calculate, 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 and you get the first component is f of x times f prime of x. The second component will be negative f of x cos theta, and the third component will be negative f of x sine theta. So there's your normal vector, and now you need the magnitude of that. So the magnitude is, so the first bit will be f squared times f prime squared, plus f squared cos squared theta, plus f squared sine squared theta, and then all of that raised to the half power. So if there's an f squared in every single term, so you can simplify that, and that just becomes f, the function f, times the square root of, and then there's also a cos squared plus sine squared. So that all simplifies, you just get f times the square root of 1 plus f prime squared. So since we now know what the magnitude of the normal vector is, we can go back to the surface area formula. Surface area is always double integral over the surface of ds, which we know converts, making the parametrization. It's the double integral over our region of the magnitude of the normal vector times dA, but we just found out what the magnitude of the normal vector is. So we know that we're given that x goes from a to b, and theta goes from 0 to 2 pi, and then we're integrating this thing. F times the square root of 1 plus f prime squared. And those are all, that's f of x, and I should fill that in. That was f of x and f prime of x, just as a reminder. Okay. So now we can easily integrate that d theta, because all of that does not have a theta in it. So relative to theta, it's just a constant. So that just becomes all of that times theta, with theta going from 0 to 2 pi. So plug that in and you get 2 pi times all that business. So it's the integral from a to b of f times the square root of 1 plus f prime squared, and then all of that dx. And this may look familiar because this is precisely the formula used in single variable calculus to find the surface area for a surface of rotation. So once again, we find that we can make a general formula for which things we've seen before are just a special case. So let me just say that so far we've looked at a bunch of different calculations for how we would do a scalar surface integral. We looked at it in general if the surface is described by a parametric formula. We also looked at one or two special cases. So we looked at the special case if z equals f of xy. Also the special case if your surface, we just looked at the special case where your surface is a surface of revolution. But in all of these cases, we know how to do sort of like the very first step of the calculation, which is to convert ds into magnitude of the normal vector times dA. So now that we know how to do, in a sense, any scalar surface integral, we can now say that any previous double integral application that we had, we can now do as a scalar surface integral application. So what were some applications that we had before? So one that we had was mass, density, and center of mass. And of course, this is in the two-dimensional case. So first, just a reminder of what we'd seen previously. So previously, we saw these formulas. So suppose that we have a flat two-dimensional sheet. There we go, make that better. With density P, whatever that function is. P as a function. And that's kilograms per meter squared. So it's like a two-dimensional density. We know how to find its mass and its two moments. So the mass M is the double integral over the region of the density dA. And we also know how to find its x moment and its y moment. So its x moment is double integral of the region of x times the density dA. And then the y moment is the double integral over the region of y times the density dA. Okay. So now we want to adapt this if our two-dimensional object is not flat in the xy plane, but rather it is a parametric surface. So what does that look like? Well, the very first update is very easy. Instead of writing dA, we simply write ds. And then the rest of it, we need to update the formula so we can calculate it. So notice, so first just focus on the first part of this equation. So the mass M is just going to be the double integral over the surface of the density ds. So notice that that's very, very similar to what we had before for the mass. So all this really says is just the density times the little bit of area of the surface. So once you set up that basic formula, we now know how to take that and convert it to an integral that we know how to do using the parametrization for the surface. We know that P, which starts out as a function of x, y, z, well, we now have a parametrization. So P, the density function, can be written parametrically. So it winds up being a function of u and v. ds, we know how to rewrite that parametrically. We take the magnitude of the normal vector times dA. And then we're going to do the double integral over the region meaning over the relevant values for u and v. And then it works out very similarly for the x moment and the y moment. And now because we're in three coordinate space, there's going to be an x moment and a y moment and a z moment. So just as a quick reminder, notice that we are in a three-dimensional space. So therefore, whatever the moment or the center of the surface is, the center is going to exist in our three coordinate space, x, y, and z. So if you want to wind up, for example, defining a center of mass, that center of mass is going to exist in three-dimensional space. Okay. So it's going to have an x moment and a y moment and a z moment. And they're all calculated in the similar fashion the way the moments are calculated. And once again, we know how to write the conversion, which is the parametrization. Okay. And then, of course, the center of mass is the usual thing. The x coordinate is x moment divided by the mass, comma y moment divided by the mass, comma z moment divided by the mass. So let's take a look at how a problem works. Okay, so here's the question. Find the mass for this sheet, and the sheet has the formula R equals 2uv, comma, u squared minus v squared, comma, u squared plus v squared. So there's the formula for your surface. Next, and the boundaries are u squared plus v squared is less than 1. And the density function, p equals x squared plus y squared. So let's find the mass. So we know basic formula, the mass m is just always going to be the double integral of the density p ds. So now we need to convert that so that we'll start converting it so that we can actually calculate this. So we know this is just the double integral over the region, and that's the region of our parameters, of P will still be the density function, but it's going to be re-expressed in our parameters. And ds converts as the magnitude of the normal vector, dA. So now we've got to figure out what these things are. So the first thing always is to make sure we have to get our parametrization. Well, we're given the parametrization. Great. What's the next thing we need? The next thing we're going to need is the two tangent vectors, take the cross product to make the normal vector. So let's do that. So notice that your first tangent vector, dr du, calculate that and you get 2v, comma 2u, comma 2u. Second tangent vector is dr dv. So calculating that, you get 2u, comma negative 2v, comma 2v. Then you need to make the normal vector, so you take the cross product. So the cross product is calculate, and you get 8uv, comma 4u squared minus 4v squared, comma negative 4u squared minus 4v squared. So there's your normal vector. Now you need the magnitude of that. So taking the magnitude, it's just going to be the first thing squared plus the second thing squared plus the third thing squared, square root of all that. And after you calculate that, some terms will, after you do the algebra, it actually simplifies a little bit. And under the radical, you get 64u squared v squared, and then 32u to the fourth plus 32v to the fourth. And being a little bit clever, you can actually simplify this further using algebra. So first of all, factoring out of 32, you'll get u to the fourth plus 2u squared v squared plus v to the fourth, and then that is just u squared plus v squared, and that itself is squared. So taking the square root of that, you just get 4 rad 2 times u squared plus v squared. And notice that there's no problem taking the square root of that because we know that u squared plus v squared has to be positive, or I should say non-negative. So after doing all that simplification, we finally have an expression for the magnitude of the normal vector. So now we can continue calculating the integral. So let's write that all out. So this becomes, so first we need to write down what is our density function. So the density function was x squared plus y squared, which we now need to write down parametrically. So x was 2uv, so square that, and then y was u squared minus v squared, so then square that. So then that all works out to be the double integral of, so multiplying all that out for the density function, you get 4u squared v squared plus u to the fourth minus 2u squared v squared plus v to the fourth. And then times the magnitude of the normal vector, which we calculated was 4 rad 2 times u squared plus v squared, and then all of that dA. We haven't yet broken down the dA because we're focusing on other stuff. That's how I choose to do it at this moment. Okay, so next, 4 rad 2 is a constant. I'll pull that out to simplify things. And so doing a little more simplification in the first factor, you just get u to the fourth plus 2 u squared v squared plus v to the fourth, and then all that times u squared plus v squared. Doing more algebra simplification, the first thing is just u squared plus v squared, all of that squared. So the whole thing just works out to be u squared plus v squared to the third power dA. Okay, so now we actually are at the point where we need to make our parametrization. We need to break it down. We need to break down dA. So notice that our region A, that region itself was described by, going back to the question, u squared plus v squared is less than 1. So that is just a filled in disk. So if we want to do an integral over a region which is a filled in disk, how are we going to want to do that? we could just use regular coordinates. But then the problem is that even if u goes from -1 to 1, v is going to go, well, there's radicals, we don't like that. We like to use polar coordinates to for a filled in, for a circle or for a disk. So re-express that in terms of polar coordinates. How does that work? Well, we know that dA, when converting to polar coordinates, dA becomes r d theta. And we know the bounds. So this disk has a radius of 1. So r is going to go from 0 to 1. And theta will go from 0 to 2 pi. So that's the first part of the parameterization. The changing of coordinates. And then the other part of the changing of coordinates is we need to say, well, we need to re-express u and v. Now, this actually works out really nicely because the basic thing is that u squared plus v squared equals r squared. But our entire integral just has a u squared plus v squared in it. So that thing is just r squared. So this is a tricky problem because you have to do, in the process of doing the integral, you have to do another change of coordinates in order to make the integral simple, shall we say. Okay. So finally, writing down our dA, converting to polar coordinates, we have this integral. So it's just the integral of r to the 6th, times r d theta, so r to the 7th. So that gives us this integral. So working it all out, there we go. So working it all out, you will wind up with there's no theta, so doing that integral will be very easy. And integrating r to the 7th dr will just give you r to the 8th over 8. And then r is on the bounds from 0 to 1. Theta will be evaluated from 0 to 2 pi. So working it all out, you'll get 4 rad 2 times 2 pi times 1/8. Simplifying, you just get rad 2 times pi. So that one was algebraically, there was a bunch of steps. It was a bit of a journey. But that is an application in order to find the mass for a surface whose formula is written parametrically. And to take that whole big problem, to break it down, let's just point out a couple of the important basic steps. First basic step, mass is always going to be the double integral over your surface of your density ds. And then we know how to convert that into our first step to convert it into a parametric form. It's going to be the double integral over the region, and that's the region for our parameters, of the density times the magnitude of the normal vector dA. So then you need to calculate the normal vector and take its magnitude, and then you'll need to set up your dA, and you also need to parametrize your density function. So magnitude of the normal vector wound up being this, and then rewriting the density function was just this. So there's rewriting the density function in u and v. Here is the norm of the magnitude of the normal vector, and then dA. So typically, if it were a slightly simpler problem, at this point, dA would just be du dv. The problem with du dv is that because the du dv region is a disk, we're going to want to actually convert those coordinates. But that's the basic idea behind how you work through the integral. And in particular, here's an application. So integrating the density will give us the mass. So just a bit of a review of the big steps of that problem. So I've got another problem here, but I feel like I've talked for long enough. So I'll just say, here's an interesting problem that you can do on your own if you want to get some practice. And what I want to jump into right now is just to wrap up by giving you a summary. So what have we covered? So suppose little bold r is a function which maps a r, which is a two-dimensional region, to S, which is a surface which itself is two-dimensional, but it lives in a three-dimensional space. So then what can we do? We know that we can construct a normal vector by taking dr du. So where our two parameters are u and v. So dr du is a tangent vector, dr dv is the other tangent vector. Their cross product will give you the normal vector. That's the first thing. Next, we know that we can find the area of the surface it's by definition the double integral over the surface of ds, but that converts to the double integral over the region of the magnitude of the normal vector dA. And then also we can generalize that to any scalar surface integral by just throwing a function in there. So the double integral over the surface of some function times ds equals the double integral over the region of your function f, which will now be written in your parameters, now in terms of your parameters u and v, again times the magnitude of the normal vector dA. Now, special case. An important special case because it comes up a lot. What if your surface is just described by z equals f of xy? Then you can use x and y as your parameters. And you can also construct a new function. You can say that g of xyz, written as z minus f of xy equals 0. And then you can construct the normal vector simply by taking the gradient of this g function. And that, as we've seen before, is just negative df dx comma negative df dy comma 1. And therefore ds, or once again, the double integral over s of ds is just the double integral over the region of magnitude of the normal vector. In this special case is just going to be square root of df dx squared plus df dy squared plus 1, and then all of that dA. And then we have an application. So an application which we saw before only for z equals f of xy, which we've now seen how to do for general parametric surfaces, which is that if f is a mass density, then doing the scalar surface integral gives you the mass of the surface. So that's a broad summary overview of all the things that we looked at today.